Doctor S. Sciences, PhD from École Polytechnique Fédérale de Lausanne. Hopefully, I'm right in my pronunciation. Yeah. So EPFL, Switzerland, in the year 2000 and 2005, respectively. He was a postdoctoral fellow at the ICSI Berkeley, USA, from April 2006 till March 2007. He is now a senior researcher at the IDIAP Research Institute, Switzerland. He is also a lecturer at EPFL. His main research interest lies in signal processing, statistical pattern recognition, artificial neural networks, and computational linguistics with applications to speech and audio processing and multimodal signal processing. He is an associate editor of the IEEE ACM transactions on audio, speech, and language processing. So today he'll be talking, his topic is on the progress of automatic speech recognition methods from knowledge-driven to data-driven. So the whole gamut of journey, what ASR has undergone, he'll shed a light on those aspects. With that, like, I request Dr. Matthew to take over the session. And thank you for accepting our invitation, sir. Yeah.
Yeah, thank you, Deepak, for the introduction. And can you all see my slides in the full screen there?
Yes, sir, but it's not full screen. If you can just make it so, that will be more legible.
Make it screen. Wait.
Maybe you need to go to the presentation.
Yeah, I did that.
Okay.
And then if I make my PowerPoint full screen, you should be able to see the PowerPoint full screen, right?
Yeah.
Is it now full screen?
I'm afraid not, sir. Are you sharing the full screen from your this thing?
Okay, let me do something. I'll make it full screen and then share it. Is that okay?
Yeah.
That makes the right way to do it.
Sure.
For presenting.
You may have to share your full, entire screen. So when you try to share your screen, it will ask you 3 options. So
yeah.
Choose the first one. Your entire screen.
Okay. Okay, I'll try. Entire screen. Okay, and okay, good. Allow, and can you see my full screen now? Is it on full screen?
It's appearing.
Yeah.
Still it's not full screen.
Please go to view and go to full screen.
View.
So kindly press function key F5.
F5.
Yeah.
Well, that's not the same on Mac, I guess.
It's not same on Mac.
Yeah. So
go to view and
okay,
see the options.
Maybe I will do something. I'll share the PDF version and start with that rather than PowerPoint. So I will do that way. Sorry. Yeah. PDF version. Open the PDF. Okay. Voilà. So this is the one. Okay. And share the entire screen. PDF. Hello. Okay. Can you see my full screen now?
Yes, sir. Yes, sir. Yeah.
Now you can see the full screen.
Now,
right?
now it's full screen. Yeah.
Okay. So I'm using my PDF version rather than PowerPoint. Okay. I'm sorry for all the small delays. As Deepak said, we're going to talk about how speech recognition methods have evolved over the years, and we can see that in some sense we were initially a bit more knowledge driven, and over the years it has moved towards we still use knowledge, but we try to use minimal as possible, and that the data from the data we try to learn as much as possible. So in this talk, I would not have so much time to go into very details of a lot of theories and detail into the theoretical aspects and so on. Having said that, my main aim is to kind of show that or demonstrate that the methods what over the years are not so very different, except for a few questions that I will try to formulate in this talk. The way you answer those kind of 4 questions, these methods emerge out of them. So the talk is organized into 4 parts. First is introduction, and then I briefly talk about knowledge-based approach. Then I talk about something called what is called instance-based approach, and then I talk about model-based approach, which is more on statistical models, which can use neural networks or Gaussians and so on. Okay, so in speech communication, as you may have already seen or already known that, okay, there is somebody who produces a voice speech, and it's recorded, and then a human can actually listen to it, and they can decipher many types of information out of it, like message, speaker identity, emotional state, even personality, gender, health status, and so on. Now, in the speech recognition point of view, we are mostly interested in the message component. And what the idea here is that, okay, you have a voice production system, which has the folds vibrate, and then the articulators move, and then that modulates the air, which is passing through the vocal tract, and we get a signal, which is here in the green. And from this, we are interested in modeling the phones, sequence of phones, words, or phrases, this kind of components, information. Now, this information is there, and this can be used for many types of, this message component can be viewed in many different ways. One way is that what we are going to focus today on is on speech recognition, where you have speech as input, and then you want text as the output. Or sometimes you want to even search for terms within an audio or speech recording, which is what we call as spoken term detection. Now that's another application, which is that the reverse of this problem, where we give text as input to a system and we want the speech as the output, which is the text-to-speech synthesis, which we may not deal, but the things we discuss in this in this presentation would still be useful for those purposes. And then the third component is, I call it a speech assessment, where you give a speech signal and you want to know whether the speech is intelligible. That is, you know what's the words, can you recognize the sounds, can you recognize the words, is it natural? It's like when you produce text-to-speech synthesis, you produce a speech output, whether it sounds like human, it's natural. Then you can ask if you're working on developing learning platforms using spoken with the speech technology. Then you can ask either proficiency or fluency and so on. These kind of questions you can ask. Even if it is pathological speech, you can ask what kind of pathological issue is coming, or is it severe or mild, or these kind of questions you can ask from that. Now, what is the fundamental question in most of these things? What I have tried to present at some point is that how to match an observed speech signal with a word hypothesis WK. I note here WK, and K is the K word hypothesis, please remember. And from a set of word hypotheses, which is a calligraphic W, I put here. And in speech recognition, what we are interested in here is that we have a speech signal and there is a set of word hypotheses, and we have to get the best matching word hypothesis, W hat. Now, this is in the simplest way we can formulate the speech recognition problem. Now, it's important to tell that this set calligraphic W is a very, very large set. Actually, it cannot even define it in a finite way. And here I put a small mathematical expression here. Of course, depending upon what you define as a match. Here I am assuming the match is high, higher the better. That means then I say arg maximum, whichever word hypothesis maximizes the match, I'm going to get the word that as the output of the speech recognition system. Now, this is the general formulation. We can take it, and from this we can start asking questions. But so the point is how we go from S to W hat, or how we match WK and S. This is what we are going to focus most of the talk here. Now, this formulation, we can simply kind of formulate it as that, okay, there is a word hypothesis, like a text I have, say my name is Matthew. I map it to a symbol sequence, a latent symbol sequence, y1, yn, and y up to n symbols are there. And I take the speech signal and I also map to a latent symbol space, and this is a shared latent symbol space from between WK and S. That's a shared space to which we are mapping. For instance, let us say I can map a word hypothesis, my name is Matthew, to character sequence like MY, NA, ME, like this. I can have a sequence. And somehow if I figure out from my speech signal that another sequence of characters like M, and maybe it makes a mistake somewhere, and so on, I get another sequence from the speech signal, I can match it, and I can define this is matching between these two simple sequences, and I can say, hey, how well they match. Now, if you go back into computer science or information theory, you can ask this question in a simpler way. This is there are 4 questions we can put here before into this. What is the shared latent symbol set, Q1? So this Y1, Y2, they are going to have a shared latent set. What is that? How are we going to map this latent, the speech signal to this latent symbol sequence B? How are we going to map the word hypothesis to a latent symbol sequence A? And how to match the 2 latent symbol sequences A and B? Now, we will I try to demonstrate here or show you that different methods actually, the way you are going to answer these 4 questions, that's where the different methods differences lie. Otherwise, the general idea is more or less same for all speech recognition methods. Now, if you ask, I want to match it to latent symbol sequences, and if you go to computer science or information theory, then you can ask this question. Is called what is called string matching, which even in your computer program, if you say string compare, that's exactly what does the string mapping. String matching, and where I have a sequence here A, C, C, D, E, and A, B, C, D, and I want to transform A, C, C, D, E into A, B, C, D, how much changes I have to make. Okay, or I have to transform A, B, C, D to A, C, C, D, E, how much changes to make. And there is this is a dynamic programming problem here. And here, basically, if you see this in the end corner, what you see, the 2 here, it says that I have to make 2 changes. Now, how do we find these 2 changes inside that? Is that you use dynamic programming, and where we have an initialization starts at 1, and it's going to end at MN, the path. And in between, we have a recursive equations going on. So there's something called local score, and then something called constraints, local constraints we have. Now, this local score is nothing but you compare if string M is equal to string N, that is, you are saying if A and A are equal, then the local score is 0. If these strings are different, then you are saying 1. And basically, for example, if you say compare this block here, you are going to compare A and B, the score is going to be 1, the local score. And then basically, these local constraints basically tell you how we can actually, this is the optimal. So the basic idea is that this is the optimal sub policies. So optimal policy is composed of optimal sub policies, and the sub policies are exactly looking at the local score and applying the local constraints. You optimize it. So the local constraints in kind of string matching is there are 3. Either you can insert, substitute, or it is perfectly matching, which is correct, or you delete. And based on these local constraints, you can compare two strings, and then you can come to this, tell that oh, I have to make 2 modifications to convert either ABCD to ACCDE, or if I want to convert ACCDE to ABCD. I have to make 2 changes. Now, if you ask this question in terms of speech recognition and other problems, this score is going to be a soft score for you. It's not going to be hard decisions like what we are trying to make here in this case, but it is going to be a soft score. So in this case, it's a distance. So in this case, lower the distance, better is the match for you. So the ideal distance is 0 for you. Now, building on this, in this string matching idea, the first approach emerged in the knowledge-based approach. So in the knowledge-based approach, the idea was that, okay, I have a speech signal. I segment this speech signal. So you would have all gone through the earlier lecture at some point, how we kind of do a frame by frame processing of speech and so on. Beyond this frame, actually, you try to segment the speech and you label each segment, give a phonetic labeling. And similarly, from the prior linguistic knowledge, you map the, based on the linguistic knowledge, you map the word hypothesis to like take a dictionary and map it to a sequence of phones. And now, once you label the speech into once you have segmented the speech and labeled, now you have 2 phonetic sequences here, for example. That's what we do, the phone knowledge. And you can match, and you do exactly what I was talking about, like a string matching, and you can come up with a match score for each word hypothesis, and you can select it. Now, here is a plot. I have taken it from one of the earliest systems, what's called hearsay, where it shows that, okay, you have a digitized waveform, you do parametric analysis, you have a segmenter and labeler, and you get a matrix with all these label sequences you want. And then from the control, what they have a syntactic predictor. That's a word hypothesis that goes to a lexicon and picks up the expected pronunciation. And then it's going to do a matching over here, and it's going to give to the controller to do a response kind of thing. So this is the basic idea that was developed initially, that where the idea was that, oh, we can segment the speech into phonetic sequences, and then we can compare these phonetic sequences and so on. Now, the difficulty of this problem was that at each stage, you are relying on mostly the knowledge. When you are segmenting the speech and parametric analysis and all those things, you are overly relying on the knowledge there. And second thing is that you are making early decisions. That means you take a speech segment and you say, oh, this is sound ah. Now, suppose your decision was wrong there, that it will be difficult for the system to recover. Now, these are the basic things about knowledge-based approach. Then came what is called, we will see the statistical approaches that came that said, hey, I can avoid like this kind of hard segmentation. I can avoid what's called hard labeling. We can deal it in a more soft manner. We don't take any early decisions. We delay the decisions until the end. that's the basic idea of statistical methods inside that. Now, having this, around this happened, this system, what I told you, knowledge-based approach, this is one of the things which emerged in like 70s and late 70s. It was very popular. Around the late 70s, again, that's another approach that emerged, was instance-based approach. Although the paper of Shako Chiba is one of the most cited paper for instance-based approach, which is called also the dynamic time warping based approach. The original idea actually even came in the very, very early 1970s, the idea. Now, in this talk also I have given some of the, what you could read perhaps to get this, the things I'm discussing in a bit more detail. So I have given some suggested readings. So in the basic idea of the instance-based approach is how we represent the word hypothesis WK. So what I talked about the knowledge-based approach, we are assuming that there is the word hypothesis is represented as in a textual form. So we write it down. Now in instance-based approach, this word hypothesis WK, when we model them into the system, they are represented by speech signal. For example, you can ask people to record each word or phrase and you store them. And then you put them together during the recognition to figure out what it is. Now, the general idea that emerged emerged was from the success we were finding with the speech transmission and speech analysis based. We were doing the speech coding approach where we were trying to separate the source and the system, and then we kind of were transmitting the source and system information over the channel, and then we were putting them together to synthesize speech back on the receiver side. So this is what was happening in the telephony. At the time they said, oh, that we can nicely, and then in the telephony, one of the most important aspect was to transmit the message. And they were saying that, hey, if we do this, we can transmit the message. Now the people started asking, oh, why don't we just parameterize it? And once you do the analysis of the speech and you separate the source and system information and all this information, why don't we parameterize it and then compare sequences of features? Now, the motivation here is what I have tried to just summarize here. So speech signal can be deconvolved into source and systems and basically synthesized back, putting those components. Now, vocal tract shape is different for different sounds. So there can be a pair of sounds here, which may not differ in the shape, but maybe in the voicing aspect. Now, so the people said, oh, why don't we parameterize the vocal tract system information, integrating some perception, speech perception knowledge, example MFCCs or PLP, and compare as the speech signal and the word hypothesis, which is again input speech signal with the word signal that corresponds to the word hypothesis. So the basic idea is that, okay, I have recorded a phrase here, WK. We basically do a short-term processing, like a frame by frame, and each frame we extract a feature, and you store the sequence of features for each of these word hypothesis, what you are having here. You take the speech signal, input speech signal, that is what you are doing during the recognition time, what you are getting, and you get this S, the speech signal S, you take it, you do a frame by frame processing, and then you extract the same features, and then you want to match the sequence of features. So just for notational point of view, the S, M, and S and W here are notating a frame of speech signal, and Y, Z and Y are denoting a feature vector, which can be a capital feature, for example, here. Now, you're going to match again, you're going to do a dynamic programming like what I discussed already for string matching. So we are going to come back to a dynamic programming here. And what is there is that in the dynamic programming, again, okay, we need a local score and a constraint to do the matching. here to match these two sequences, which can be of two different lengths. We want to match, and we need this local score. And the local score, what happens here is it depends on the what feature you use. So if you are using a capsule features, you can use like a Euclidean distance between the feature vectors. If you're using linear prediction coefficient, then you use eta Cora distance. And if you use spectral information, you use eta Cora cyto distance. So the local score depends upon the feature, how you parameterized this from the speech signal to Z1, S1 to Z1, or W1K to Y1K, what kind of parameterization you do. Based on that, you decide this local score. And the local constraint is like a monotonic constraint, like you go forward in time and you don't come back in time. Actually, you move forward. And now here I have drawn a local constraint where it says that at this block at time m in the test sequences and and time n frame n in the reference sequence, I could have come from the previous what is called a test frame, but I could have stayed in the same frame as the reference, or I could have come from the previous test frame and the previous reference frame, or previous test frame and 2 frames before in the reference here. Now, this is a local constraint we have, and in this local constraint, there is nothing so magical about it, in the sense that Sako and Shiba, if you take the paper, they discuss so many different kind of local constraints, what I have shown. In this local constraint, you can even assign some kind of cost for each of these transitions, what you are making here. So there's a lot of constraints you can try in these kind of things, but here I do one of them, which is a popular one, which can handle nicely like a doubling of if m is like n is m is like 2 times n kind of situation you can handle in this case. So in this local constraint, within a word, you can have a local constraint. So for example, let us say a word hypothesis, a word K, you have this local constraints within a word. Now this local constraint, what happens is when you go across the words, when we are looking for, when you're doing a speech recognition, you're not going to look only one word. When you do a connected word or continuous speech recognition, you have to look for what will be the next word in that case. And there you have that it comes from the last state of any other word K dash to the word K, first frame of the word K, you have this constraint of transition. So you have a crossword constraint. And now this here, actually here, you can associate a cost, because there's it's not always possible. A K dash, a word K dash follows a K is not always equally probable for you. So you can add a cost, which we can formalize it in the HMM based kind of talk I have talked in, which is going to come across. There you can formalize this cost as what is called language model, which tells you what is the probability to transit from word K dash to K. You can compute it, you can estimate it, and you can actually use that as a cost. Now, given this, you can actually do now a speech recognition now where you actually have to pick what is called the word hypothesis that minimizes the score, because here we are dealing with Euclidean distance and eta Cora distance and eta Cora cyto distance. So you are trying to minimize those distances, and you're going to pick the word hypothesis that best matches the speech signal S. Now, in this case, we come back and we formulate the 4 questions I asked. So here the short-term feature vectors are the latent symbols for you. The parameterization approach, whatever way you use, the feature vector, they become the latent symbols. However, these symbols, the set of symbols is undefined. In fact, we cannot even define it in a closed set manner. Because the features we extract, although we say we are extracting vocal tract features and so on, these features are not unique in terms of the sound. They're still susceptible to variabilities. I'll show some examples in the next 2 slides for them. Then the Q2, where you have to map the speech input S speech to the sequence of latent symbols, you have to do short-term speech processing, basically base feature extraction. So you're going to get a sequence of features. You're going to do the same with the WK, the word hypothesis, which is again stored as a speech signal. And you're going to apply this dynamic programming, which I discussed in the last slide, last 2 slides, with a local score and local constraint. You're going to match them, and then you're going to pick the one which is going to be the more having the lowest distance in this case. Now, as I said, this Q1, let's focus a little bit on this question of Q1. Why I'm saying this is difficult to define this spectral feature to be a unique feature for each sound. Here is an example. I give a case where the sustained vowel A has been produced by a male and a female and a child. And now you can observe that actually each of them have a different, so here if you have followed Prasanna's lecture and other thing before, these are my formants like F1, F2, the green one for F1, F2 for male, then we have the female F1 and F2, then a child has an F1 and F2, and you see that they don't have exactly the same you cannot get exactly the same representation out of this spectral, although the male, female, and the child have spoken the same sustained vowel here for us inside that. Now, this is what we call interspeaker variability. Again, we can go this argument, you can extend it from other point. The moment you add noise a little bit to the speech signal, again, estimation of the spectrum changes. So your feature extraction is not like a unique representation, which is with respect to the sound that has been produced. Similarly, within a speaker, there can be variations. So here is this like a sustained vowel produced by speaker, female speaker, R produced by female speaker 3 times. And you can, again, you say even the same speaker could also introduce changes. As a consequence, actually, it is very difficult to get this the perfect feature. If you have it, I think we have nailed many problems. It is not there. So the summary of this instance-based approach is that it works well for speaker dependent. As I said, like if you have one speaker and you build only for that speaker, this kind of system, it would work because we probably know how to handle this kind of small inter-speaker variability. It is clean and controlled conditions. It can be applied. In the late 90s, this approach was there on the phones where we had the option to dial names by just speaking the name. So you basically what you do is to do that you first store like a few instances of the names you want to call, and then during dialing you just say the name and the system will do what I have just described here, and it will pick the name for you. Generalization across speakers and conditions is highly challenging. Reference templates typically represent word units or even phrases. So every new word needs a new reference template for us. So defining them into phonetics things is not easy. So we usually use word as a unit here. Since you are going to store this this whole speech waveform and the sequence of features and so on, it needs also a large amount of CPU and memory. It imposes memory requirements and CPU requirements. Large amount of memory and CPU will need it. One of the pros of this approach is that there's no training needed here. What training here is that the reference hypothesis, all you're asking is that to ask people to produce, speak, and you record and you store it. That's it. There's no training. So, and you can just go for the recognition. Now, as I said that for this approach to succeed really well, if you can find a short-term feature processing based feature representation or any other feature representation you can find, whether you do today with the feature learning, like feature engineering using neural networks and so on, if we are able to find a feature that is so much representative of the linguistic unit for us, like a phones or syllable, and is robust to any other undesirable variable like the speaker changes, environmental changes, or emotional state changes, and so on. If we can make them robust to all of those aspects, then this method is a very simple method to implement and to be used. Now, this is a part of the research that has to undergo that is still of interest if people would like to pursue this problem further. Now, from instance-based to model-based approach, so I'm going to talk about what is called the hidden Markov model based approach. I'm not going to go into very details of this theory and all those things, because here the next talk you will be hearing from Professor Samudra Vijaya. He is going to talk about statistical modeling and so on. Again, I'm going to trying to show that whatever we see, this symbol matching, and that also is there in the hidden Markov models, except that we are going to do in a probabilistic way there. And so what we do in a probabilistic way is that we formulate a statistical criteria for that. So what we say is that what we want to do is we want to find the word hypothesis that has the highest posterior probability, that is the speech signal S and the WK, whichever word hypothesis has the highest posterior probability, that is the word hypothesis WK given S. I want to estimate that probability, and whichever I will estimate for all the hypotheses, we will say, and basically we'll say whichever hypothesis has the most high probability, there I will take that as the word hypothesis. Now, estimating this quantity is what we call as posterior based approach, this quantity. And estimation of this is a very challenging problem, and this is where neural networks are trying to come up with solutions towards that, which is what Deepak will talk a bit more on this point. On the right side, people decided, well, we can go to the Bayes rule and we can estimate the joint likelihood of between the word hypothesis and S, and we can assume that this same criteria, we can make it to a maximum likelihood estimation problem, assuming that the denominator quantity, the likelihood of the speech observation S, is not depending on any class. So basically, we can take the decision based on the numerator. And that's what is the likelihood-based approach for us. Now, again, in the speech signal, what we are going to do, keep in mind, is that we have a speech signal. We are going to do short-term processing, every window, S1, SM, and SM. And then from this window, each window, you are going to extract a feature, whether it is MFCC, PLP capture coefficient, or filter bank energies, whichever what you want to estimate. This is X1, XM are the features, you are getting it. So this is what you're getting for the signal S, which is the thing. And then for the word hypothesis, WK, for example, you have a WK here, and it is a sequence of words. For example, the cat, you go to the dictionary and you are going to pick up based on if you are using a phonetic dictionary, it is going to say that the is, but the D here is the followed by E, followed by a short pause between the two words. Then it can, cat is like a term, like that. So you have a word hypothesis representation. So you have these two representations, just keep in mind, because we are going to now see how these two representations are going to get matched in a probabilistic way. Now, in the likelihood-based approach, when we write it, so we can, note that I am writing as here, but then once we extract the features, we can only deal with what is called the X, the feature sequence. So we can estimate the joint likelihood of the word hypothesis and the X here. Now the theta A, theta L are the parameters here for me, which I have to some way model during the training or estimate during the training process. Given these things, these parameters, and the observation X during the recognition, I will have to find the WK. That's a problem here. Now, these two things can be again divided here. And one is called acoustic modeling for us. The other is called language model, which is the prior probability. Now, the language model are estimated using discrete Markov models, and this likelihood of the observation given the word hypothesis is coming out of an acoustic model. It is coming through hidden Markov models for us. Now, this is just a factoring, so there is no magic here. You can also write the other way around, but this is what we are going to, because these two quantities can be estimated relatively easy. Now, once you want to estimate this prior WK given theta L is the parameter, just understand that. Given these parameters, we want to estimate the probability of the whole sequence. That we do with what is called Markovian assumptions in that case, so which has a discrete Markov model where there is the set of states are nothing but the words in the vocabulary for you, and each of those words are connected to each other, so they have some transition that if I define the set of words, the transitions between them and the initial conditions, I can define this model completely inside that. So now we can do some simple statistical factoring here. Basically, you can write the probability of word K as, you know, each of this. Sorry, there's a mistake over here. I equal to J 3. Yeah. Sorry, there's a mistake over the notation here in the product, but anyway, so the point is that any word K, the ith position word is going to depend upon I minus 1 to 1 on that. And you can write this, this as a small multiplication factor. The problem is that the more deeper you go into the word hypothesis, you have more and more history to model. And this is a challenge for you. So what you do is you have to make a Markovian assumption that's in the diagram, is that you say any word at a particular position I is going to only depend on I minus 1. This is what is bigram. If you say it depends on I minus 1 and I minus 2, it becomes your trigram. And now these probabilities, what we talk about here, they can be estimated with like books or web and so on. You can use all the textual resources, or you can even use the speech recognition. You will have that when you build the systems, you have transcriptions. So from those transcriptions, you can estimate this quantity. And there are two popular approaches to go across. Initially, we came up with this idea of n-grams, which was purely based on counting. You can these probabilities can be estimated using counting. You can use how to deal with unseen and all methods. We have developed methods for discounting, back off, or interpolation methods we developed for them. or if you don't have enough counts, how you deal for that. There are smoothing methods that are there. And more recently, what we have come across is we can estimate the same this kind of conditional probabilities, word transition probabilities, using neural networks. Now you have this word transition probability. Now we have this estimation of the acoustic model, which is the likelihood of the observation sequence X given the word sequence WK. Here is where we start introducing the hidden Markov model. I'm skipping a lot of steps here for you. If you make the first order Markov assumption and independent identically distributed, these two assumptions, you make it. Based on that, you can write down the estimation of the likelihood of this likelihood as nothing but emission likelihood, which is P of xm given qm, times the transition probability between the states for you. And an approximate solution here would replace, which is the Viterbi solution. Instead of summation, you can make it the best path solution, and you can get this likelihood as an estimated, this likelihood is estimated as the best path within this sequence of HMM states. Now, this quantity P of X emission likelihood, again, there's a small factorization that goes around, which is only you basically assume that this space XM and QM are basically having a intermediate space, a symbol space AD for you, and you can express this likelihood as multiplication of two quantities, which is estimation of the feature vector xm given the latent symbol ad, and p of and the mapping of this HMM state to this latent symbol ad for it. This we can factor it out, and this is there in the paper which I have cited in the beginning of this portion of the presentation. You can find it over there, the derivation of this. And the HMM state, they can represent, for example, context-independent forms. Like you have cat, you say, well, I want to model k, and t independently without any context information, or I model them as context-dependent for me, like k, sorry, I made a mistake. K is followed by and k is preceded by k, followed by t, and t is preceded by so we can model them in context. So this they can represent this kind of information. And then what happens is that we want to map to this AD. So, and let's assume that I can represent a vector of probabilities P of 1 given QM and to AD at any time, and it can take any of this symbol, like if I take this as a context independent thing, the L and K is nothing but the or E or a short pause or k or a or t. And this mapping, what we are finding here, it can be prior knowledge driven in the case of context independent phones. It can be both prior knowledge and data driven, which is basically this AD is nothing but the clustered content dependent states. And this mapping is typically one-to-one between the states, what the phones, they represent the states, and the latent symbol AD. It's a Kronecker delta distribution. So this is an example I provide here. Suppose we have this word, a sequence called silence, stop, and that, and silence. Then we have silence as to s, t, o, p, then the silence. And then we have a context dependent mapping. And these context dependent mappings are getting mapped to some kind of clustered context dependent states or phones, here, and they are having a number M1, M2, M23, M94 like this, and this can be running into thousands for you, a few thousands. And this mapping from this state, this context dependent to this symbols is defined. The clustered context dependent phone is defined through a decision tree. So it has a unique mapping, and that is why I'm saying it's a Kronecker delta distribution. So if we take this P, whatever notated as P, as a space, let us say I have a 5,000 clustered context dependent states or phones. This S sir preceded by silence and followed by T is going to map to one of them uniquely, and that's what the decision tree does. And so it's a Kronecker data distribution for you. Now you will see in the next lectures and others, which some of them will deal again more in detail. In this case, this likelihood of the latent symbol AD given the observation XM. Sorry, that's a small comma there. That's a mistake there over there. That can come from, for you, this likelihood can come from Gaussians or neural networks. So Gaussians can directly estimate this likelihood quantity. In the neural network, you actually estimate what is called pseudo likelihood or what called scale likelihood. So what neural network gives you is the posterior. So you train a classifier that classifies all this, the D space latent symbols for you. You get the posterior probabilities. That is what the neural network will give us output. You scale it by the priors, and then you get this pseudo likelihoods. So these two quantities, this one can come from like a decision tree. That's what I try to show, or knowledge-based approach. Again, it's a table, lookup table for us. And this information, the likelihood information here, is coming from the either you use Gaussians or neural network to estimate this likelihood there. Now, once you have that, you can, I am expanding it for the Viterbi algorithm here. You can write down in the this whole equation in the log space, and in the log space you can see that this is your local score, what you comes up, and whatever the transition probabilities, they are going to be your weight on each transition. So the transitions until now we discussed like DTW or string matching, I was saying they are not weighted. I mean, they are having equal weights, basically. Here, they are going to be weighted by the transition probabilities. Now, so the basic thing, coming back to the matching problem again, here is that we have a local score, DMN, which is nothing but the Kronecker delta distribution Y and K, which is with dot product between that and the likelihood vector. You are going to get that. And that is your local score, the log likelihood there. And then you have to do the minimum, and the local constraints, they come from the topology you use for HMMs. For example, I have drawn here a topology where either you can be on the same state or you could have come from the previous state. So that is, you remain in the same state, or you could have come from the previous state. And each of these transitions are going to have a cost, which is the transition probabilities here for you. Now, this is the dynamic programming you can apply here when you estimate this Viterbi likelihood or best approximate likelihood path. So this is what you're applying here inside that. And then in this case, what happens is that now suppose if these two states are coming from this, let us say the left state is the last state of some word, and the next state is the first state of some another word, then that will actually, the state transition probabilities will incorporate the language model for you. That's the same idea what I explained in the DTW. It is the basic idea that the transition between the first frame of a word and the last frame of another word in the DTW, it is modeling the word kind of constraints of which words can follow which words. And similarly, the transition more probabilities here, they incorporate your language model information when you look at across the words. Yeah. Now, if we go back again, we ask these 4 questions in this point. Is that typically in currently, if you take HMM-based speech recognition, we are using context-dependent phones and so on. So the latent symbol space is typically a clustered context-dependent subword units, which can be like 5,000, 10,000 kind of space for you. The estimation of emission likelihood, that is how you go from the speech signal S to these latent symbols. You can go through a Gaussian mixture model or artificial neural networks, subspace GMMs, or you want to do vector quantization, or you want to do KNN. There are many different ways to do this estimation for this. Then how you map the word hypothesis WK to these latent symbols A1, AD, AD. It is typically in the context dependent. When you model the states as context dependent phones, then it comes through your decision tree, and typically it is a canonical data distribution. Having said that, this distribution can be also probabilistics. There are extensions of that. And the local score of the dynamic programming is nothing but your the estimation, this likelihood vector VM, and this the Kronecker data distribution. You take the dot product, and that the logarithm of that minus logarithm of that is your local score here. And the transition, the constraint, the local constraints are defined by the HMM topology. So if you draw a different topology of HMM, the constraints can change. So whatever you saw in the Sarkov-Chiba, you take it and try to visualize it in a different HMM constraints if you want to. So if you see them, they can have different topologies, can have different local constraints, and these transitions can have unequal cost, which is what the transition probability. These transition probabilities may not be equal. It can be 0.5, 0.5. Okay, no, they're same, but they can be different. And as I said, keep in mind that in the case of speech recognition and other problems, what we are trying to do is that between the words, you are going to get the word transition probabilities. Now, to summarize this figure is that we want to actually estimate this posterior probability of words sequence given X, but what we're happening is we go through the Bayes rule, and we make an assumption that this likelihood vector in the denominator is independent of the class. So we can take decision just based on the numerator. And that is what we are trying to do here. Is the figure here. So you have a speech signal and you get a sequence of spectral features, which are the X for you. From that, you get the emission likelihoods here, which is what is this quantity for us, this quantity. And you have a lexicon that tells you how you can put all these phones in a sequence to create words, and the grammar or the language model that tells you how probably is one word following another word. You put them all and you pass it to a decoder, and then you get a sequence of recognized words. And then if you want to interpret further, our speech recognition stops over here. Further interpretation, you will need passes, like for example, where the punctuation comes, or where the, where is the stop, where is the comma. These kind of things would need to be added later for it to be more readable for us. Now, whatever I showed here, it looks so complex for us, but we can take a very simpler view on this problem, that the language model, in a way, can be seen as a word hypothesis generator. So the language model is kind of a word hypothesis generator for you, and it can generate any kind of word sequences for you with some probability there. And the speech signal, we can we estimate this likelihood vectors inside that, and we are going to match this sequence of what is called Kronecker delta distributions with the sequence of the likelihood vectors for each of those hypotheses, and we try to make a decision which word hypothesis is the best. Yeah. Now, to do this, all those things, we cannot. I have shown here as a closed set. Only K, as I said, there is this set is a big set of hypotheses. Literally, we cannot even define them. So we take some heuristic approaches like beam search and stack decoding, and also there are some other aspects such as these likelihoods usually are going to be scaled, and the language model probabilities also are going to have some kind of scaling. We have some other kind of penalties like word insertion penalties that are going to be introduced. But the general idea is that the language model is like a hypothesis generator for you. From that, you use the lexical knowledge and the decision trees to come to the sequence of Kronecker delta distributions, and that is what you're trying to match with the sequence of likelihood vectors. Now, what has happened in the recent trends? I may not be able to go in very details of these things. So let us take a simple case, the word at. So here I'm notating in terms of characters A and followed by T, a simpler case here. Now we are trying to solve this through this estimation of joint likelihood between the speech signal and the word hypothesis. Here is at simply here for us. Now, more and more recently, the more recent works and current trends is that how we can make it more and more is like string matching or symbolic way of doing it. And there are kind of two prominent way of going it in this is that there's what is called connection CTC here and RNN transducer. In both cases, what you are assuming is that's an empty symbol. We are employing an empty symbols. And basically, in the case of CTC, the policy is that the as much as possible empty symbols and fewer symbols of A and T, so that you can just quickly do a string matching directly. In RNNT, the basic thing is that there are many you can actually observe a symbol only once, whereas in CTC you can observe many times, like A followed by empty symbol, then it can be T followed by TT followed by empty symbol. But here it will be empty symbol, or A empty symbol, then T, like that you can observe. So only one occurrence, and that occurs at the transition, and that's why it's called transducer. When you leave this empty symbol state, you are emitting a symbol, and that is A and T. And this is, again, once you have this, the formulation straight away comes into string matching formulation, these formulations. And then what you do is in doing this, you are also moving away from this joint likelihood estimation problem to posterior probability estimation problem, and that is what is the current trends in speech recognition. So what I try to present here is the thing that in speech recognition, one of the core question is matching a word hypothesis with a speech signal. That is a fundamental problem. And invariably, in almost all methods, it is a latent symbol sequence matching problem. It can be, the latent symbol sequence can be linguistically based on linguistic knowledge or data driven, or it can be even spectral based, as we saw in the case of instance based ASR. Now, different ASR methods differ mainly in terms of what are the set of latent symbols, how are we going to map the speech signal to the latent symbols? How are we going to map the word sequences in a word hypothesis to the latent symbol? And how are we going to match these two sequences, and with what cost function we match? And that mainly is that what makes these approaches different for us. Thank you.
Thank you, sir. Thank you, sir. Thank you for this wonderful presentation. Yeah. Now I would like to consider taking questions from the audience.
Yeah.
Yes, anyone? Yes, participants, if you have some questions, then please you can discuss with the professor. Okay, so then we don't have any questions.
So I can ask a few questions and people understand. Okay, so you all know string matching well? Because I would like to see how what I have given, if understood or not. So everybody would have done somewhere string matching. The bottom line here, what we try to show is that here I try to present is that the same string matching formulation is extended across different ways, like whether we do knowledge-based approach or spectral-based approach, or you do hidden marker model, or even if you do the end-to-end neural network-based approach, which Deepak will talk a bit more. If you have understood, if you see that relation, then you kind of see that you may have to focus your attention on those four subset of problems I'm talking about. And if you can, and if you are doing a research, you may want to find how your method or approach is differing from those four subset of problems I have explained there inside that. So that's my point here.
Okay, so I have one question, not question, sir. I just want some suggestions from you, sir. So, what is your take-home message for the participants? So, considering that we are moving from non-AI era to AI era.
Yeah.
So, what will be your take-home message for the participants in this field, in automatic speech recognition?
In my, I think I don't know if we can say we are moving from non-AI to AI era. The reason I say that because most of the things what we do with neural networks, hidden marker models, and all these things, they have in a big way speech recognition, and speech has actually contributed to that for us. So what has changed actually is mainly the thing I talked in the very last slide in my presentation here. So basically, we are still remaining in the same formulations of like latent symbol matchings and all those space. We are trying to match them. what we have done, what we have mainly seen is that we have tried to go from this joint likelihood estimation to this posterior probability estimation problem. This is a very challenging problem, actually. Just estimating this posterior probability is an estimation of a sequence of the posterior probability of a sequence given another sequence is a very challenging problem, and that is exactly what has changed, in my opinion, in the field of speech recognition. So, otherwise, most of the methods we are dealing are have been evolved, like take neural networks, hidden Markov models, Gaussian mixtures, all these things, they pretty much evolved with speech. So I the main thing, in my opinion, is that what is changing is going from this likelihood joint likelihood estimation to this posterior conditional posterior probability estimation problem, and that's what it has changed mainly here for us.
Yes, thank you, sir. Yes, participants. So, if anyone of you don't have any question, then okay. Okay, thank you, sir, for this.
Thank you,
Any-
Sebastian. Yeah.
And thank you for this wonderful presentation, sir. It was really brilliant, and I'm sure that some, may not be all, but some of the participants will get benefit from this presentation. Yeah. So yeah, once again, I thank you, sir, for
Thank
finding
you.
time from your biggest schedule and presenting this one.
Thank you. Yeah.
Sir.
Okay, then. Bye, Shivashankar, and all the best to everybody. Then, bye.
Thank you, sir. Okay.
Bye.
Okay, so we'll now meet around maybe 1 hour, around 1:50 p.m. because the next session starts at 2 p.m. So we'll meet around 1:50 p.m. And I've already shared attendance, attendance or feedback link in the chat box. Please do give the attendance by 1 p.m.